Hello friends, welcome to this lecture from the Hydrology series. In this lecture we'll be studying about runoff, which is basically an important concept in engineering hydrology. I will be taking this subject based on the book written by K. Subramanya. It's a highly popular book and it's currently used by almost all students of civil engineering for their college studies as well as for their exam preparation. So we have used this book, and somewhere we will be using the images and text directly from this book. So let us begin. Now first of all, let us understand what is runoff. To say it in very simple terms, runoff means draining or flowing of precipitation from catchment area through a surface channel. It means that suppose you have a mountain here or some highland and stream flow. So what happens that if rainfall is taking place, so those water which goes like this over land and meets this channel, and the channel subsequently meets any stream, that thing is called as runoff. So basically it's a flowing of precipitation from a catchment area. I have told you in earlier lectures that what is catchment area and what is precipitation. Precipitation will be mostly used as rainfall in this context and in this lecture henceforth. There are basically two components of runoff. First is your overland flow. What happens that if water flows directly on the surface and it meets channel, then it is called as overland flow. But what happens that if it's percolate beneath the surface and if it goes like this and then it meets your stream or water channel flow, then it is called as subsurface flow, or it's also known as interflow. The first is this and second one is it also known as quick return flow. So let me show you through an example or through the diagram used in this book, which will make you quite clear about this concept. Let us look at this example. In this, what happens that you have precipitation, it is your rainfall is falling here, and then after rainfall takes overland flow, that is water flowing over the land and then meeting in a affluent stream. But there is also one phenomena which is known as through flow, which I have told you, that is it is also called a subsurface flow and or interflow or seepage. And third is your if the water meets the groundwater and groundwater then meets the affluent stream, then it is known as base flow. So we have three concepts here. But first is overland flow, second is through flow or subsurface flow, and third is your base flow. Base flow is that part of contribution which comes through the groundwater channel. Let us summarize once again what we have studied. So we have first called as overland flow, which we are clear about what is that. Second is that we have interflow, that is flow beneath the surface, and this is flow over the surface. Basically this is the main differentiating criteria here. So for interflow we have two categories, that is prompt interflow and delayed interflow. So what is prompt interflow? Prompt interflow is that where there is least time lag between infiltration and outflow is known as prompt interflow, and where the time taken is too large. For example, if water meets this groundwater table and then it takes a very long time and then it meets your effluent stream, then it will be called as delayed interflow. And if the water takes this route, that is just beneath the surface, it moves very quickly and then it meets effluent stream, then it will be called as prompt interflow. So the groundwater follows a complicated and long path of travel and ultimately reaches the surface. The time lag, that is difference in the time between entry into soil and outflow, is very large, because it will come to groundwater and then it will move through water, air, soil voids, and then it will reach here. So time taken is very larger, for it is known as delayed interflow. Now based on the time delay between precipitation and runoff, the runoff is classified into two categories. For classifying runoff we have two categories, and they are direct runoff, direct, indirect, or you can say base flow. So what is direct runoff? Direct runoff is that part of runoff which enters the stream immediately after the rainfall. So basically it includes surface runoff, prompt interflow, and other which, and that rainfall which falls directly on the stream. So you have three types of runoff which contribute to direct runoff. Let me tell you once again, that is surface runoff, prompt interflow, that is water reaching quickly beneath the ground surface, and that part of water which falls directly on the stream. So you have all these three terms will be counted in direct runoff. And for base flow is that delayed flow which reaches the stream as groundwater, essentially as groundwater. That is, first the water reaches the groundwater and then groundwater reaches the stream. So this is known as base flow. So we have divided runoff into two categories, that is direct runoff and base flow. So base flow you can say essentially as groundwater. This is groundwater flow. If groundwater is contributing to any stream or river, then it is called as base flow. And all the water contributed through direct runoff is called as basically through surface flow or prompt interflow, or through directly falling into stream is called as a direct runoff. So base flow, base flow we have said it is groundwater, and we will be using this concept in hydrograph or derivation of hydrograph also. So kindly pay attention to this concept, it is going to be a critical concept. So next we look at concept which is called as natural flow. What happens that there is no man-made structure, or there is no diversion work on a river or any way in its catchment basin or in any channel, then runoff will represent the basin characteristics or catchment, and everything other will contribute to the runoff. So we can get an idea about the catchment, its size, or rainfall characteristics. So it is a good indicator of such conditions. But if there is any human intervention, such as your diversion or reservoir, then you will see that rainfall or runoff characteristic is not what you will get without such intervention. So these such cases are not the representative of natural flow, or you can say virgin flow. Hydrograph is basically a plot of discharge in a stream against time. So depending upon the unit of time involved, we can say that there are annual hydrograph, or monthly, or seasonal, or flood hydrograph. So we can calculate hydrograph if on any of these time unit depending on our use. Annual hydrograph show variation of daily, weekly, or 10-day mean flows over an year. Monthly hydrograph show variation of daily mean flow over a month. Seasonal hydrograph show variation of discharge in a particular season, such as monsoon. Flood is that which is the representative of hydrograph due to a storm flow, due to a storm over catchment. So if there is any storm, then we can plot a flood hydrograph for that given storm. A simple concept is water year, which we use is water year. It is that years is like financial year, or your budget year, or new year, calendar year. So similarly we have water year. It is that year is followed from June 1st to 31st of calendar year, 31st of May for the next calendar year. So you have basically water year will be like 1st June 2018 to 31st May 2019. A study of annual hydrograph of streams enable one to classify streams into essentially three types. First is your perennial flow, perennial, you can say perennial stream. In Hindi we see it as nirantar. It means that one which always carries some flow. So if there is no flow from river from its upstream, then there is groundwater flow contributing to that stream. So you can say that perennial river always carries some water, it always have some flow, and there is always some groundwater contribution. Intermittent flow has some limited contribution from limited contribution from groundwater. And during wet season, the water table is above the stream, and there is contribution of base flow to the stream flow. But during dry season, water table drops to a level lower than that of stream bed. What it is saying that suppose you have your stream bed, this is your bed of stream, and in wet season, in rainy season, you have your groundwater level. This is your groundwater level, and there is contribution to the river. But in dry season like this, what happens that this groundwater table drops below your river bed, so there is no contribution to river stream. Therefore this is known as intermittent, that there is sometimes there is contribution and sometimes there are no contribution through groundwater. Third concept is your ephemeral stream. An ephemeral stream is one which does not have any base flow contribution. Zero base flow contribution, you can say zero base flow. That is, there is no contribution from groundwater, and the stream dries soon after the end of the storm flow. If there is flood, then its water will be there in the stream. If there is no flood or no rainfall, there will be no water in such stream. So we have looked at three classification of streams: perennial, intermittent, and ephemeral. Now we also look at flow characteristic of stream and what are the factors on which flow characteristics of stream depend. The first factor affecting the distribution of runoff is your type of precipitation. Type of precipitation. It is if there is more precipitation or if there is more rainfall, the runoff will be more. So it's quite simple. Second is, you can say, the intensity. If intensity is high, then infiltration will be less and also seepage will be less and runoff will be more. If more water falls in a shorter amount of time, that is intensity is high, then runoff will be relatively higher. In the third concept, you can say rainfall duration. That is, if rainfall falls for a longer time, then runoff will be greater. It's quite simple. And the rainfall distribution, that is, if you can say runoff is highly affected by distribution of rainfall, uniformly distribution may lead to delayed runoff. Then at the same volume falling over localized part of catchment, that is, if your rainfall is distributed, then runoff may be less, and if your rainfall is localized, then runoff is going to be relatively greater. Now there is one more thing, which is one more factor which is called as catchment factor or catchment. Catchment, you know, that area which drains into a river, that is your, suppose this is mouth of river, then all this area draining here will be your catchment area. So catchment factors such as shape, topography, and soil type, these things remain constant over long period of time while others change radically. So shape of catchment area influences the time of concentration. That is, if time of concentration, basically first you have to understand TC, that is time of concentration. Time of concentration is that in which the entire catchment starts contributing to runoff. What it means that if rainfall is taking at all the place at the same time, suppose rainfall is taking place in all over the area at the same time, then these area will be contributing to water here after a relatively greater time than these areas, because these areas will soon be starting to contribute to the water and these areas will take more time. Therefore the TC's time of concentration is that time after which all the area, this complete area, starts contributing to your channel. or stream. Therefore, you can say that if your catchment is long, narrow, then it will yield low value of form. It will yield generally lower peak runoff. First, let us understand some concept about shape factor or catchment factor. The shape of catchment area influences the time of concentration of catchment. So if your catchment area is long, that is your catchment area is like this, long and narrow, then your peak will be less, runoff will be less. But if your catchment area is like this, very axial length is it's less, then your certainly the runoff is going to be more. So we have a thing called form factor, that is its axial length divided by its average width of catchment by its axial length. It is width by L, W by L, you can say form factor. And one more concept is like that compactness. What it says that derived by the periphery of the watershed, by the circumference of circle which is equal in area to the catchment area. So if your shape is like this, now you measure the periphery or the length. So let us say that L is the length of this or periphery of this area, and C is the circumference of equivalent area, equivalent circle. Equivalent circle is that circle whose area is equal to this area of this shape. So this will be called as compactness factor. Compactness factor influences runoff in such a way that you can say that lower the value of coefficient, that lower the value of this compactness factor, the more rapidly water is likely to be discharged from catchment area via the mainstream. So the concept is like this: if your value is low, that is your L is your this periphery length is less and C is more. C is the circumference of equivalent circle. So if this thing is more, that is the shape is less than circle, the shape deviates away from the circle, because if this is perfectly circle, then what will happen that this L will be equal to C and the compactness factor will be equal to 1. So we need the value to be less than 1 in order to increase the runoff. The next thing is geology. We can easily understand this thing that coarse texture sandy soils will tend to give rise to little runoff. That is, there will be more percolation or infiltration in coarse grain because it has high permeability. Voids are bigger, basically voids are bigger, and on the other hand, fine grained soils, compact clay soil will tend to yield more surface runoff because clay have low permeability. Now next factor is vegetation. Vegetation, you can understand it simply like that: if there is vegetation cover on the ground surface, and the rain runoff is likely to be less because water will not be allowed to go down the slope by the vegetation cover. And if the ground is bare, there is nothing on the surface, then water will quickly run down the slope. So it's inversely proportional to vegetation cover. And a drainage network, if there is closely spaced stream flow which will allow efficient drainage of water, then the runoff will be more. Runoff will be greater if closely spaced stream channels are present. Movement of storm also has some influence on the runoff characteristic, like when storm is moving upstream, that is when storm is moving away from the mouth of the catchment basin, it is moving upstream, then runoff peak will be less. And if storm is moving downstream, then peak will be more, because as it comes down, all the water that has drained on its previous journey will start to come down, and as soon as it reaches mouth of the basin, all the water will start contributing at basically at the same time. So time of concentration will be basically less. So you can say that if movement takes place in the direction moves upstream, then the peak will be less, and if storm moves downward, then peak will be more. Basin yield refers to the quantity of water available from a stream at a given point over a specified duration of time. That is, the duration of time in the definition of yield would normally be a month or longer. It is expressed in terms of volume but not discharge. That is, you can say a basin yield. Yield means something that is given out. So this quantity is in volume or meter cube. So it will be integration of your discharge function with respect to time from time t1 to t2. It gives an estimate of basin yield, that how much water can be given by the basin. Therefore you can say that basin yield is summation of continuous hydrograph of flow at its outlets over the specified time period. So this concept will be made clear when we understand what is hydrograph and how it is plotted. But for now you can say that basin yield is that suppose how much this is your basin area, this is your area, then how much water can be given in by this area or catchment, this is called as your basin yield. So yield of a stream is basically related to the natural flow in river, but if the water is diverted from stream for other purposes like drinking, irrigation, some part of diverted water returns to hydrological catchment, which is known as return flow, which I have told you earlier also, that if your dam creates some diversion on a river and it later meets this diversion later meets your river, then it is called as a return flow. How runoff can be determined? We can determine it using empirical formulas, and we can also determine using curves and tables, also from runoff coefficient method, from infiltration method, from water set. There are a lot of methods for determining runoff, but for our chapter we will be looking at a method of establishing relationship between rainfall and runoff. It is a rainfall runoff equation, which is basically given like this: R is runoff is equal to A, P is precipitation plus B, where A and B are constant to be determined, and values of A is like this: N is your total number of observations at summation PR minus summation P summation R divided by N times summation P square minus whole square of summation P, and B is summation R minus summation A minus A times summation P divided by N. And for this you have to establish coefficient of relation between them, and R is given by the value of R should lie between 0 to 1. The greater it, the more it's near to unity, the good relationship constant is. Relationship is said to be a good indicator if value of R is greater than 0.6, and we have to note that this R can only be positive value. It is a well-known fact that stream flow varies over a water year, that the flow in a river or channel is not constant. So one of the popular method of studying the stream flow variability is through flow duration curves. What is flow duration curve? Here you can see that this curve is your flow duration curve, that it represents the daily discharge or your monthly discharge or whatever frequency one takes, and with respect to that discharge you have the percentage probability of that discharge being equaled or exceeded. It is a plot of discharge against percentage of time the flow was equaled or exceeded. and this curve is also known as, you can say, discharge frequency curve. So how do we calculate this? What are the steps of making this discharge frequency curve, and we can get, and what are the analysis this can be used to derive? We will be looking henceforth. So first of all, what is done, that stream flow data. So data set is arranged in descending order. For example, the value of discharge of Q 350 meter cube per second, and then it has 250, then 100, then 75. So this data is arranged in descending order, and then the data sets are given their order number. For example, this is order number 1, for this order number 2, 3, 4, similarly like this. And then what happens, that the total number of data sets are n. So if total number of data sets are n, then percentage probability, or you can say percentage probability of the flow magnitude being equal or exceeded is for that magnitude. For suppose for 250 we have to calculate, then we will put the value of m, the order of that magnitude from here, from the list that we have generated earlier here, and then n is our total number of data sets plus 1 into 100. So by this we will get your percentage probability, and we will plot it here, and our discharge we will plot on the y-axis, and then we will generate a curve. If data sets are more, then we will have what we say, that log scale if it is required. So what are the other associated analysis we can do from here is like, you can see that for perennial river, that is the river which always have some groundwater contribution, for this you can say this discharge, that is 50 cubic meter per, that the probability of discharge 50 cubic meter per second being equal or exceeded is 100%. So this is known as dependable flow, means you can always depend on this value, that at least this much amount of water will be there in the river stream for perennial rivers. But for intermittent or ephemeral rivers, we say that as with time decreases or increases, you can say, for example, for 250 cubic meter per second you have 10%, and for let us say for 50 cubic meter per second you have 40% dependable flow. So these rivers do not have any amount of value for discharge for which there is 100% dependable flow. Means it simply means that there is no value of discharge in such cases or in such rivers where you will get 100% dependable flow, that is PP. There is no value of discharge in these rivers. On an comfortable position, we can say that for these rivers dependable flow is 0, 100% dependable flow is 0 cubic meter per second. We can see some of characteristics of this flow duration curve which are of great importance. But we can see that slope of the flow duration curve depends on the interval of data selected. For example, a daily stream flow data gives steeper curve because it has high variation than a monthly data for the same stream. It is due to the smoothing of small peaks in monthly data. Presence of reservoir in a stream considerably modifies the Basin flow that we have seen earlier, that it basically changes the peak value of runoff, and it basically hides the actual natural flow of that catchment basin. The virgin flow duration, when the plotted against log paper probability, plots as a straight line at least over the central region. From this property, the various coefficient expressing the variability of flow in a stream can be developed for description and comparison of different streams. For what we are seeing here, we will be looking through an example or through a graph. This is a graph representing the effect of reservoir regulation. That is, when the water is diverted through a reservoir or a dam, then what happens in this graph, this discharge frequency graph is shown here. For example, for natural flow, you can see this line is your natural flow, this is representing this line. But for flow with regulation, you have smoothing of your peak. Basically your this discharge value becomes constant, almost becomes a horizontal line. This is why, because first of all the water is stored, is allowed to reach a certain level. Then it is on the discretion of humans to allow whatever water they want to let off in the stream, or minimum water, the value for which the storage or the city demands are there. So such a flow regulation influences discharge frequency graph in such a way that the slope of the graph is reduced. In fact, it becomes zero in second case, that is flow with regulation. The next factor affecting this graph is it is masking of chronological sequence of occurrence. That is, let us say that a discharge of 100,000 cubic meter per second in a stream will have the same percentage whether it occurred in January or July. This aspect is serious handicap. That means it does not take into consideration that when this flow has taken place, you will get the same probability even in, suppose, say monsoon season or in January. There is no way to tell for what time of year this percentage probability is valid or like that. So this is a handicap of, or we say drawback of, discharge frequency curve or flow duration curve. These are some of the uses of flow duration curve, such as, first of all, you can use it to calculate your dependable flow, that is PP, as we have seen earlier, that how much percentage of water is equal or exceeded for a given discharge. And you can also use to calculate characteristic potential of river, that is from all the given graphs you can calculate the discharge accumulate at a particular amount of time, or we can also calculate the percentage of discharge that will be available even in the driest of the season, that is for PP 100% dependable flow, or other hydropower potential, that how much water will be at least available in the dry season for irrigation purposes or hydropower electric purposes. So it is a great use in such cases. And you can also use to design drainage system, as we have seen that in what season and in what time how much water will be available. So how much percentage, what is the probability of such discharge occurring in a river will be used for designing the drainage system. You can also use to study about flood control for a given river, and that the value of discharge, that the value of Q which is likely to exceed it, and by how much percentage this value of Q is likely to be exceeded. So while designing structures or flood mitigation techniques, you can use this flow duration curve for your advantage. Flow mass curve is basically a plot of cumulative discharge against time. So first of all, let us understand what does cumulative discharge means. It says, for example, at time t is equal to time, and here you have Q, and here you have QCM, cumulative discharge. So at time 0 your discharge is 0, cumulative discharge is 0. At time 2 hours, so let us say it's 8 cubic meter per second, and then it will be 8. At 4, instantaneous discharge is your, suppose, 6, then it will be 8 plus 6 14. At 6 it's 5, then the value will be 4 plus 5 19. So cumulative discharge means at that particular time it is a summation of that instantaneous discharge plus all the discharges basically above it. So flow mass curve will be a plot of cumulative discharge against times, as we have seen, and the ordinate of that discharge is the integral of discharge function with respect to time from t is equal to t0 to time t. So for given time t, the ordinate of volume is given by this integration equation. So similarly, if you take the differential of this volume with respect to time will give the slope of the curve, that is flow mass curve, and it will be equal to that instantaneous, that is the instantaneous discharge, that is the rate of flow at that time, at that instant. Based on our concept of flow mass curve, now we will be looking at the calculation of storage volume for a given reservoir. So what we do in this concept is that we draw two lines, that is demand line and supply line, and the difference between these two lines is called storage. The maximum of storage in the dry spells, in different dry spells, is taken as the maximum storage capacity required for the reservoir to meet the demand of city whichever it is catering to. So what we do is we consider the reservoir, the stream whose mass curve is plotted here, and if it is assumed that the reservoir is full at the beginning of a dry period, that is when the inflow rate is less and then the withdrawal rate, the maximum amount of water drawn from the storage is the difference, is the cumulative difference between supply and demand, that is this. So what we will say that storage S is maximum of summation, the summation of demand, all the demands, and minus summation of all the supply. So you will require to store the water only if your demand exceeds your supply system, which is what happens in most of the cases. So what we have that let us suppose that this is your time. At this point, this is your this line. First of all, you have to see that this is your supply line. So at this reach, that is when the supply is maximum in this at this time. So what you do is that you draw a tangent to this line. So this line will be called as, demand line. Tangent at the reach at the starting of the season will represent the maximum demand, or the maximum demand that is possible for that given reservoir, that we cannot demand more than what has came in the reservoir. But over the time, what will happen, that demand will suppose stay constant, but supply will continuously reduce because of dry season or less rainfall. But what happens that here the gap is increasing, that this gap here is less, here it is increasing, and this is your maximum gap S1. And then after rainy season, it again goes to another level and another high, and then again it starts to reduce. This is your cumulative graph. Suppose we are doing this flow mass curve in, as we have seen earlier, in cumulative terms. It is the summation of all the values up till now. So at this point also you have to draw your tangent to represent the demand line. This is your demand line of second season, demand 2, let us say, and we have given this as demand 1. So maximum difference between demand and supply, that is S2, here it will occur, that is here we will get the maximum difference between demand and supply. Here, this is your continuous supply line. S1, S2, maximum of S1 and S2 will be your storage for a given reservoir. This concept is important and it is continuously asked in exams and other competitive exams as well as in college exams. So it's very simple, that is you have to calculate maximum of the 2 storage capacity or 3 storage capacity, whatever is given, and then that will be the storage for the given reservoir. And for calculating the storage, you have to draw the tangent to the highest reach point and then calculate the difference at the maximum ordinate at this level where the difference is maximum. So that will be the storage for that season, and again you have to repeat this process for then another season where we have another set of values. So after doing this, you have 3-4 values, and the maximum of that will be your storage capacity. It's quite clear. So you will get all sorts of questions. Basically large numerical questions will come from this concept, because it's easy, but you have to maintain the data and you have to arrange, you have to calculate accumulation, cumulative values, and then you have to plot and then draw tangent, then calculate your intercept, that is this is your intercept, and then calculate storage accordingly. So you have to take care of all these things, otherwise this is not a quite difficult concept to understand, but it's relatively much asked in the examination, and is relevant for every aspect of examination wherever you are studying or whatever college or institution or country you are in. We will look at one more concept in this related thing, that is your maintainable demand. What is this? That the problem of determining the maximum demand rate can be maintained by given storage volume can also be solved by using a mass curve. In this case, tangents are drawn from the ridges of mass curve across the next valley at various slopes. The demand line that requires just the given storage is the proper demand that can be sustained by the reservoir in the dry period. What is to be done in this case is that you have, for calculating maintainable demand, we have to first of all calculate the storage capacity of our reservoir, and then from storage capacity we have to calculate what is the maximum demand that can be allowed. And what we have done is something different earlier. In this case, in calculation of maximum storage, we have taken the demand as fixed, then we have calculated storage. And in this case we are taking storage fixed, storage value of reservoir as fixed, and then we are calculating the demand. Here demand was given and we have calculated storage, so it's quite clear. Now how do we calculate maintainable demand? What happens that first of all you draw tangent to various ridges. What we do that for a given storage value, suppose we have designed a reservoir, and we tell the city, you are dam authority, and you tell your city counterparts that this is the maximum, that S is the maximum value of storage that you can do with your calculations, and S, and beyond that you cannot do anything. So based on S you are required to calculate how much demand can be allowed, or how much maximum demand can a given reservoir sustain. So this is basically a reverse calculation as compared to this case. This is your calculation of storage capacity, and this is calculation of maintainable demand with a given capacity. So how do we do this? First of all, we draw tangent at ridge point, at this point, as we have done earlier. Now you know tangent we have drawn, but we know that S we have to keep S as fixed. So we draw tangent at this line because this is our lowest supply. This point is your lowest supply for a given season. But if for a given tangent, if for a given slope, basically for a given line, if S is okay, you draw different line from this. You just do not draw one line, you draw this, you draw this, you draw this, and you select one of those lines for which this difference is exactly equal to S. That is, the intercept between demand line and supply line is equal to S. You choose that demand. Similarly, for in this case also you draw different intercepts. You draw different slope at this given point U2 at ridge line, and then you select that demand line for which the difference is exactly equal to demand and supply is exactly equal to S. So this is quite clear. And then we, after calculating various demand line, for example you have Q2 here and Q1 here, the demand line for which the value is lowest is called as maintainable demand. And here the S value, S was maximum of S1 and S2, S3, but here your Q is minimum of Q1, Q2, Q3, like this, because it's just logical thinking and it's inverse of this, because we cannot allow more demand than what we can have in our storage. So if one of you take one thing as your constraint, you can calculate other thing. Here storage was not our constraint. Here we have to fulfill the demand, but here we have to take into consideration that storage is fixed. Therefore these two concepts are important Here we have calculated our storage capacity, and here we have calculated our maintainable demand. Some of the points which are worth noting in this case is that the vertical distance between two successive tangents to a mass curve at ridge will represent the wasted water over spillway. For example, this value, will represent your wasted water over spillway, because it will not be required. You will limit your demand to this. So if it goes above it, it will not be your required. Therefore, it represents the spillway. It represents the wasted water over a spillway. A demand line must intersect the mass curve if reservoir is to refill. And if there is no intersection of demand line and mass curve, that means there is insufficient inflow of water. And after looking all these things, I think you have got a fair amount of idea about how calculation of storage value is done, and what are different concepts associated with it. Now we will move to next concept. Next concept is the concept of variable demand. Earlier we have assumed that our demand is constant, and then we have calculated storage capacity of reservoir based on the constant demand. But what happens that in real life scenarios your demand is not constant, because for example, suppose take cropping season and other industrial requirements, they vary from time to time, and in such cases your demand cannot be constant. So what we do, we calculate a mass curve of demand. That is, we calculate cumulative demand over time with respect to chronological sequence. We calculate, we add all the demands of that time and all the demands before it, and then we superimpose on the mass curve of flow. That is, flow is that volume of water which we are getting in our reservoir, and demand is that which we need to supply to the town or city. So what we do is like, this is our mass curve of flow, that is this much amount of water is flowing in our reservoir, and this we have calculated in the same time period. We have calculated this mass curve of demand, and then we have superimposed this curve on this curve. So right now what we get is that we get variable intercepts. For example, intercept in this month, this is your March, this is your February, this is your January. So all these are your variable intercepts. So what happens that the maximum intercept, this is your maximum intercept. So this is taken as the maximum of all the intercepts that we get from this variable use line, or you can also call it as regulation diagram of a reservoir. Now we look at next concept, which is an important thing to understand. It is called a Sequent peak algorithm concept. What happens is that the mass curve method of estimating minimum storage capacity to meet a specified demand pattern, as we have seen earlier, has number of different forms of use in its practical application. So what is this concept of Sequent peak algorithm? In this we calculate net flow volume, that how much volume is there in the reservoir. So xi is your inflow volume and di is your demand at the ith period. I is your period, and xi is your inflow volume minus outflow volume di. This is your outflow, this is xi is inflow, and subtracting these two we get inflow volume. And in this case we have assumed the data to be available for n consecutive periods. It can be either day wise, month wise, or whatever period you want to take. So it is not necessary that they be of uniform length, but for all the practical purposes we take it at uniform. For example, 1 month, 2 month, 3 month, or whatever duration we want to take. So if your inflow is more than your outflow, then it means that there will be increase in storage, as simple as that. But if your outflow is more than your inflow, it means the storage will be depleted. So it's quite a simple concept. I think you have understood. Next we look at this graph, at how we have to calculate the reservoir capacity from the Sequent peak algorithm. So this thing, net flow volume, what we do is we plot this thing, whatever value we get from subtracting this, we plot like this P1. For positive values we plot above, for negative values we plot below. So this is your curve of residual mass curve, that how much water has left. This is your cumulative residual mass curve. Here you will see that there are peaks P1, P2, P3, and there are troughs. Troughs are low point, and P1, P2, P3 are high point. So you will see that there are seasons when storage is there, and there are some times when your demand or your difference net flow volume is very less. So how should you calculate your storage will depend on these P1, T1, P2, T2, P3, T3, and likewise. So what we will do in such cases, we do is one thing, that we calculate cumulative net flow volume, that is on this axis. This axis is the cumulative value of this xi minus di with respect to your time. And after plotting this graph, we locate first our first peak, that is P1, which is P1 here. Then we locate lowest trough between, and then we locate our next peak P2. So we have located two peaks, and in between two peaks we have to locate the lowest possible point, that is the lowest trough, and which in this case is T1. This is, so first we will calculate P1 and P2, and then in between P1 P2 we will look at T1. So we will calculate P1 minus T1 in the first step. This is your first step. Now come to the second step. In this, what we will do, we will start with P2, that is second Sequent peak, and we will look for P3. Now we have found two peaks, and in between two highest peaks you will have to locate your lowest trough, that is T2. After you have found T2, your next step will be to subtract P2 minus T2. This is your second step. Likewise, you have to do all n number of steps for whatever values you are calculating. You have plotted this graph for whatever number of cycle. Basically this is your cycle list. So we have to repeat the procedure for all Sequent peaks available in 2n periods. That is, we have to determine Sequent peaks Pj corresponding Tj and Gh storage. So what will be the reservoir storage capacity? It is given by, storage capacity is given by the formula S is maximum of Pj minus Tj. That is your peak, that is the maximum of Sequent peaks minus your lowest trough, corresponding lowest trough. So S storage will be your maximum of whatever values you get calculating by using this equation. One thing to note here is we have taken base period, base length of 2n years. 2n means this will be your base length. For example, from here to whatever cycle you are calculating, this will be your 2n, where n is your number of years of record. Why it is done so? This is because if n years of data are available, then inflow and demand are assumed to repeat in cyclic progression. That means your inflow and demand will, suppose your n for 10 years you have your demand and inflow, then after 10 years again the same pattern will repeat. So it is to be noted that in historical data this leads to an implicit assumption that future flows will not contain a more severe drought than what has already been included in data. That it means that if you have calculated this storage reservoir for this base period of 10 years, then there will not be a severe storm than what has been included in the data. But this assumption is not correct. So what we do is that we repeat the cycle for n additional years to arrive at our desired minimum storage requirement. That is why our base length is of 2n years. 2n years in the given Sequent peak algorithm method of calculating storage reservoir. Next topic we are looking at is about droughts. Drought means basically less or less rainfall in a given year, and you can also say that it's a disaster. It's kind of a natural disaster, and it is basically characterized by deficient supply of moisture. So generally moisture is obtained by rainfall, and if there is low or very less rainfall, then we have situation similar to what we say as drought. But how much percentage of water should be available to, or should be deficient to classify area as drought, we will be looking at it very shortly. So basically, once again, we define drought as a climatic anomaly characterized by a deficient supply of moisture. This may result from subnormal rainfall over large regions, causing below natural availability of water over a long period of time. So if this is your ground surface, okay, if rainfall is falling, so what happens that there is percolation and water is available as moisture below the ground surface. No rainfalls take place, then there will not be any water for groundwater moisture, ground moisture, and there will not be any supply of moisture to the roots of tree that are in the vicinity of this region. So ultimately what will happen that all the such plants and trees will end up drying, and there will be a shortage of food and other water related resources. That one thing to note about drought is that unlike flood, which happen very in a short amount of time, the droughts are of creeping kind, and they develop in a region over a length of time. That is, it takes the effect of drought to appear over region quite a bit of time, and its effects are even more dangerous than you can say flood, because there is large scale devastation and starvation and of basically humans as well as cattle, and absolutely everything is finished. There is no groundwater, there is nothing to eat, and there is no water to drink. So this situation is very harmful for our ecological balance as well. We will look at classification, then we will see what are the drought mitigation techniques and how we are dealing with such situations and how we can prevent occurrence of drought. Hydrological drought is said to occur when there is depletion of surface water and groundwater. The consequences are drying up of tanks and reservoirs, rivers, cessation of springs, and groundwater level falls drastically. So such conditions are called as hydrological drought. Means there is depletion of wherever there is water already present on the ground or below the ground surface. And in meteorological drought, what happens that there is no precipitation or rainfall beyond certain limit, that is when the deficiency is greater than 25%. And agricultural drought is that when the soil moisture and rainfall are inadequate during growing season to support healthy crop to grow to maturity. That is, as we have looked at, for tree to grow you need moisture in the ground surface, below the ground surface, near the roots. So if during the growth period of plant there is no adequate soil moisture to support healthy crop to grow to maturity, then we call it as agricultural drought. We have already seen about what is called as meteorological drought. Now we will look in detail explanation about classification of this drought. So Indian Meteorological Department IMD has adopted the following criteria for you can say subclassification of meteorological drought. It is said that if deficiency and classification of this drought. So if deficiency is less than 25%, then it's no drought. There is no drought. If it's greater than 25, basically 26 to 50%, then we say you have moderate drought. And if deficiency is greater than 50%, then drought condition is very severe. If drought occurs in an area, let us say Bikaner area in Rajasthan, and here we say that if the probability of occurring drought is between 0.2 to 0.4%, area is classified as drought prone area, means there is high probability of drought occurring in this area if the probability falls between 0.2 to 0.4. Now if the probability of occurrence of drought at an area is greater than 0.4, if suppose P is greater than 0.4, then this is called as chronically drought prone area. In India, if a year is considered to be drought year only if the area affected by moderate or severe drought is more than 20% of total area of country. For India, an year is said to be drought year if the 20% of total area of the country has experienced moderate or severe drought in that given area. For example, in year 2013, if the drought affected areas are 20% or more than the total area of country, then that year is called as drought year for our country India. From a hydrologist point of view, drought means that below average values of stream flow, that which results in tanks, reservoir, groundwater and soil moisture drying up, or such a hydrological drought has 4 components, that is magnitude, duration, that is for how much time there was such condition prevailing, and severity, that is cumulative amount of deficiency, and frequency of occurrence, that how frequently such conditions occur. After looking at all these 4 parameters, we can say, or we can classify that whether there is hydrological drought or not. The beginning of hydrological drought is difficult to determine because this is a creeping phenomena. However, at the end of drought, when adequate rainfall saturates the soil mass and restores the stream flow, the reservoir content to normal values is relatively easy to determine. In the studies of hydrological drought, different techniques have to be adopted for study, that is surface water deficit, groundwater deficit. You can say the surface water aspects of drought is essentially related to stream, and for agricultural purposes, if the amount of available moisture is ground is not sufficient for crops to grow, then we classify it as agricultural drought. So in this drought we use some terms. First term is aridity index, that is which is PET minus AET divided by PET into 100. Here PET is potential evapotranspiration. Potential, that is how much water can be used if the sufficient moisture is always available in the ground surface, below the ground surface, that is potential evapotranspiration. AET is actual evapotranspiration, that is how much water has been available or how much water amount of soil moisture has been used by the roots of the plant. So we define agricultural drought based on the such values of AI. So here we have AI and here we have class. If AI is 0 or negative, then the class is non-arid. If it's 1 to 25, then we have classification as mild arid. If it's 26 to 50, then class is moderate, and if it's more than 50, then you have severe arid region or season. The departure of aridity index from its corresponding normal value is called as AI anomaly, which represents moisture shortage. And as we have seen the classification based on AI, this is our classification of aridity. Now we look at what are the different techniques of drought measurement. So if you have meteorological drought, then what will happen? It creates water cycle imbalance. So what are the different types of tackling meteorological drought? It's like you can do cloud seeding, that is for rainfall to occur. The most of the common technique is cloud seeding. and evaporation control. For hydrological drought control, for hydrological drought, the consequence is your reduction of water supply. So what we have to do is that water harvesting, and we have to develop and manage our groundwater potential, and we have to develop various methods of harvesting water. We have to also look at in situ moisture conservation methods, and we have to use economically water in irrigation practices. One of the method, we have to economically use water in drip irrigation and sprinkler irrigation. So these are some of the methods in hydrological drought management. For agricultural methods, we have to, again, we can employ water harvesting techniques, and also we can opt for changing the land of our crop. For example, change in land use, that is the purpose for which the land is currently being used, or the crops which is currently being grown on this land should be used to see the effect of such measure in order to tackle agricultural drought. So we can also create water bodies. We can also reduce evaporation from soil and water surfaces, and as usual, afforestation is one of the measures. We have to look also for sand dune stabilization in such arid areas, and there are n number of methods, but for our engineering hydrology series, this much information is sufficient. There is also some information on water harvesting. You can look up into water, for example, your rooftop water harvesting, or harvesting of small ground surface area, flood water harvesting with storage or without storage. So how these are done, how the catchment is made, and what all you can do to harvest the rainwater. So these are topics of their own detail and depth and coverage, but for our information, this much quantity is sufficient, and I hope you have understood the basic of this chapter. I am developing the series on civil engineering topics first, then we will move to electronics and other subjects. But for now, if you want any improvement or you have any suggestion, kindly leave it in comments. And if you want to give any feedback, or you want me to improve on some topics, and for any other purposes, kindly subscribe and kindly like the videos that you have seen, because it really takes a lot of hard work, and through your subscription and likes, we will get motivated to make more of such educational videos, absolutely free of cost on YouTube platform, which will reach to most of the students studying civil engineering and other topics that we will be bringing in this series. So kindly give us motivation and some subscription, so that we may continue this journey further. I hope that this will be an enjoyable journey, because as we know that sharing is like learning. I am learning, so I will be your companion and guide through this whole series, and let us see how this goes. So thank you for now. Good luck.